Welcome to everybody. We are back again here with new lesson about structures. Today we're talking about of pure bending acting on a beam. On your screen you can see a portion of beam and we can see a side view of a beam and a front view of a beam and a 3D view of this beam. But now we can explore all these stuff on this our virtual page. On this beam, in this first case, we are no pure bending is applied to the beam, and we can see some letters that stay to identify our limits of the piece of the beam that we take in account today. So the piece of the beam that we take today is this with highlighted with the black pen. The left hand edge is individuated from the letter M-I-N. Instead, the right hand edge is individuated from the letter P-G-Q. So Y and Z axis are the axis of this beam clearly, but Y is the vertical axis and is also the symmetrical axis of this beam. Instead, X axis is our neutral axis of the beam. The 3D view of this beam can clarify how this reference frame is taken. Z is in the direction of longitudinal fiber of this beam, Y is in the vertical direction, and at last X is in the direction of the neutral axis in this case. So the fiber is indicated from the line drawn in orange, and its limits are S and T. The other fiber, I and G, are the fiber that lie on the neutral axis in this case. The neutral axis is important axis because along this axis and along the neutral plane also, the stresses and the strains are equal to 0. But in the front view, we can see also the strip area that is indicated from the delta A. We're going to take it from a few minutes for some explanation to derive effectively the stress due to bending moment applied on the beam. So we can see also two dimensions, y1 and y2. y1 is the distance of the upper part of the beam to the neutral axis. Instead, y2 is the distance of the bottom part of the beam to the neutral axis. This is a mean line. This is the distance. Y plus is the distance of the mean line of the this strip area. Y plus because it's in the direction the positive y. So this portion of beam highlighted in black has a length of dz, here written in the blue with the blue pen. So here no bending is applied on the beam. The beam is at rest, but when we apply some bending moment on a beam, we obtain something like this. So in this case, we have a moment that produces a compression of the upper fiber. So all these are upper fiber, all these are the bottom fiber. These upper fiber are compressed due to the bending acting on the beam, and bottom fiber are in tension. So, but before of this explanation, we see some other stuff. First thing, we see the radius vector that indicated with the letter R, and we can note also this point C. So C is the rotational center of the beam and r is the radius, because in this case we assume that the deformation assumed of the beam delta theta is small. The shape of deformation is quite similar to a circular deformation, so r is the radius of this circle that identify the deformation of the beam. So if you can see, if you continue the draw of this beam, you can note that it's quite similar a circular shape. So, but we can assume also important assumption that the first assumption is that the bending stress is such that the cross section are not deformed after the stress due to bending, and this cross section remain planar and normal to the longitudinal fiber of the beam. The second assumption is that the material which is made the beam is linearly elastic, so means that the material obey to the Hooke law. So we have in this case sigma z is equal to E times epsilon z. E is the modulo of Young. So this is the Hooke law. After these two important assumptions, we can see that the neutral plane in this case is deformed. I mean that how said before, the deformation of this neutral plane is quite similar to circular. We can see also the these h are now not more straight as before, but after the bending stress, when the bending is equal to 0, these MIN and PGQ age come back normal to the plane, neutral plane, and clearly to the fiber. So we can see also another important consideration to do is that the fiber ST individuated before, now for the bending moment on the beam is shorter than before, but the fiber NKQ is the longer fiber of this piece of beam. That is always this piece, portion of beam. The MP fiber is the shorter fiber of this portion, because the upper fiber are in compression, the bottom fiber are in tension. The only fiber that remain of the length equal to dz, that is the initial length of the whole fiber when the bending is not acting, is the fiber IOG, because it's lied on the neutral plane. On the neutral plane, we said before that the stresses and strains are equal to 0. So the only fiber that remain with length equal to the initial length is the fiber IOG. Now we can derive some relations. Due to the bending, we say that we have a change in length of our fiber, especially for our fiber, reference fiber, that is ST, but the same things are subject to the fiber MP and fiber NKQ. The first thing we consider, the first case, the bending moment acting as the example in this figure, let's say figure 1. The case is this. So the strain is the ratio between the change in length divided by the initial length. So epsilon z is equal to change in length divided by initial length. In this case, our change in length who is. So, first thing, we must derive the length of this fiber ST. How can derive this length? We can remember that when I have a small angle, d theta, and a certain radius r, I can express ds, the length of a general thing, as equal to radius r times d theta, or delta theta. In Italian we say delta theta. In this case, ds is our st, so st length, the new st length is equal to radius r minus this distance y. So is radius r minus y, and this is our, let's say, the new radius is this r minus y times delta theta. This is the new length of the st, but the change in length is delta L, that is equal to L final minus L initial. L final is this new length, radius r minus y times delta theta minus L initial, that is delta z. So, and this is the real change in length divided by, now it's more simple if I write this delta L divided by LE. So we can see this formula, everything. Now I can write here epsilon z is equal to delta L, that is radius minus y times delta theta minus delta z divided by delta z. We can make some simple calculus. So r times d theta minus y times d theta minus dz divided by dz, epsilon z is equal. But dz, the length dz, that is now this is our delta z in this case, is equal to radius times delta theta. So I can write here dz as r d theta minus y d theta as before, minus radius times d theta divided by r radius times d theta. We can simplify now for r d theta and obtain that this strain epsilon z is equal to minus y times d theta divided by r times d theta. D theta and d theta we can simplify, and so we obtain that the strain is equal minus y over r. So we derive the strain in this case for the bending moment that is in this case anti-clockwise. So if you see from here, is anti-clockwise from the T point, and the as said before, ST, our reference fiber, is in compression. So this is equation number 2. Let's say equation number 2. How tell us this equation? We see also a minus sign. So if y is measured than 0, epsilon z is minus than 0. Is when the y is minor than 0, epsilon z is measured than 0. So in this case, all the fiber in direction of y positive axis. I drew it a little bit on the left hand, y, in direction of y positive y, indicated from the red arrow. In this case, all these fibers are changing length, that these fibers are shorter than the initial fiber. These fibers have a length that is shorter than the initial its length. While for all the fibers placed in the direction of negative y, so in this direction, all the fibers have a length that is measure of the initial length. So this strain is positive in this case. So delta L, this is delta L, means that is positive. So final length minus initial length is measured than 0 in this case. In this case is obvious, is clearly because the bottom fiber are in tension for the due to bending moment acting like this. In the other case, this case, when the bending moment is clockwise, if see from this edge, we have a similar consideration to do. So epsilon z is equal always delta L divided by L initial, but in this case the reference fiber is in tension. Okay, so the initial length is lower than the final length. So delta L is measured in 0 because we can see here that the ST length, who is the ST length in this case? ST length is the radius r, but plus y in this case, times d theta. And the initial length is always, delta z is always equal to r times d theta. So Ez is equal to r plus y times d theta minus r times d theta divided by r times d theta. If you make some simple calculus, obtain this relation, so epsilon y divided by r. In this case, for all the fiber placed in direction y positive y measured than 0, epsilon z is measured than 0. For all the fibers placed in the bottom part of the y in the direction of negative y minor than 0, epsilon z is minor than 0. So this fiber have a length, have delta L measured than 0. This fiber have delta L minus than 0 because the LF here is measured than L initial. Here instead LF is minor of L initial. So this is the consideration to do in this case. But now we choose one case, but the other case is similar, follows the similar consideration. For me, in this lecture, I can choose this case when the bending moment is anti-clockwise, so the reference fiber ST is in compression. The delta L of the ST is minus than 0. So final length of the ST is minor of the initial length of the ST. So now we can derive another important consideration, that is the first moment of the area of the cross section is equal to 0. Why? In Italian the first moment of the area is the momento statico. I speak a little bit in Italian for the Italian user. In questo caso dobbiamo dimostrare che il momento statico della nostra sezione di drive rispetto, diciamo, al piano neutro e all'asse neutro deve essere uguale a 0. Vediamo adesso perché. So to derive this consideration, we can consider that the normal force that acting on the fiber ST, in this case along all the length of the fiber ST, this normal force, we can express the F is equal to sigma z times the A. Okay, but on the beam now are acting all a pure bending moment, so the F is equal to the integral on the surface A of sigma z times the A is equal to 0. Sigma z is equal to Young module times epsilon z. But epsilon z we have reached before from the equation number 2, that is equal to E is the module of Young. Epsilon z is equal minus y over r sigma z. We place this equation in the third equation to obtain a fourth equation, that is in this case F is equal to minus Young module divided by r, extracting from the integral sign, because the modulo, the Young module and the radius are a constant quantities. Integral on surface A of y times dA is equal to 0. So tell us that integral on surface A of y times dA is equal to 0. This is the first moment of area of the cross section. In Italian say momento statico. So the first moment of area of the cross section with respect to the normal plane and the in this case of the also the neutral axis is equal to 0, because there are no axial force on our beam but only a pure bending moment. Now we can consider this view, this front view with the neutral axis and the symmetrical axis, that is y, and this strip area called delta A. So the force that acting on this little strip of area is a compression force, clearly. So we can write that this compression force is equal to sigma z times delta A, this portion over. Remember that is not integral, because delta A is a little bit an area, a strip area that is quite small, but sigma z times an area is equal to a force. Now we can see this consideration. Let's take a portion of beam straight, just to look this thing. This is point T and this is point S. Here acting a FC, on the other side, to respond to FC, to the equilibrium, we obtain this other F psi. But consider the F psi on T axis, F psi on the T side, where the T is placed. So we have FC is in the direction of negative Z. So here we obtain FC is equal minus sigma Z times delta A. This is equal to sigma Z is equal to minus modulo of Young times y over r, over radius. So we have minus E modulo of Young y divided by r times delta A. So we obtain that FC is equal to modulo of Young times y divided by r times delta A. This is FC at T side. The FC at S side is equal minus FC at T side, so is minus E times y divided by r times delta A. These two forces produce also a moment respect to the neutral axis. So the moment product to Fc on T side is equal to Fc on T side times what? Times this quantity, this is the y, this distance y, so we have fst times y, and we obtain y is positive because is in direction the positive y, and we obtain module of Young times y to the second power, or y squared, divided by radius times delta A, and moment on the S side is equal to minus m on T side, so is equal to minus e times y squared y over radius times delta A. So we have this another important equation, that is the fifth equation, mt and mness. So we have also this fifth equation, that, and this is let's say the sixth equation, the forces and the moments. Now clearly ms and Fc on S side are the force and moment that responds to Fs on T side and M on T side to equilibrium. So to the rotational equilibrium, we can see that the moment applied, M, the total moment applied, bending moment applied, plus the moment applied on T side must be equal to 0 to the equilibrium. We can obtain that M is equal to minus M on T side, that is equal minus the now we can integrate on a surface A of E divided by R times y squared times the A in this case. So we integrate on all the area of our cross section. This was a strip area, a little bit portion of area of our cross section. This is all the cross section area. So we can obtain that the M is equal to E divided by radius integral of on the surface A of y squared times dA. But this quantity is the second moment of area, that in Italian is called momento d'inerzia, but in English is also known as inertia moment about x-axis. So we can obtain minus Young module divided by R times EX. We can write that the moment divided the moment of inertia about x-axis is equal to minus module of Young divided by R. But we say that sigma z is equal module of Young times Ez, that is equal to minus E times y over R. The quantity, the ratio of module of Young divided by radius, we can express as minus E divided by R is equal to sigma z divided by y. So M bending moment divided by moment of inertia is equal to sigma z divided by y. So we can finally obtain the expression for the stress due to the bending moment. So sigma z is equal to m times y divided by axx. This is the last equation of this relation. That is the seventh equation. So this is the classic equation that we see everybody and everywhere, that tell us in this case, so for the example shown here, y1 and y2. y1 is in direction of positive y, and y2 is in direction of negative y. If the moment applied in this case is, if the moment applied in this example is minus the zero, in this case is counterclockwise for me, and y1 is measured than zero, we obtain a sigma z related to y1 that is minus zero. For the other y, so moment is always minor than zero, y2 is measured than zero, and we obtain that sigma z related to y2 is measured then here is minor than zero. We obtain that sigma z is measured than zero. The unit of this quantity sigma z is expressed in the international system as Newton divided by millimeter at square. So this is sigma z unit of measure. But we can do another consideration, that is this. If we see this equation, we can note that the moment divided by E times xx is equal minus 1 over r. So if I put this equation here, we say that minus 1 over r, that is a curvature that we can express as k is equal to the moment, the bending moment acting on a beam, divided by E times axx. So this is the flexural stiffness of the beam. So the higher is the flexural stiffness, the lower the lower the curvature and the higher the radius will be. So that means that when this quantity is very high, the curvature is very low and the radius is very high. And in this case we can translate this thing as, when the beam has a high flexural stiffness, is much difficult for us to bend it. So we have a thing like this, a straight portion of wing. That means that if these quantities is much higher, the curvature is much lower. You see a simple straight piece, and the radius is much higher. So this r goes to let's say to infinity. Also see in the extreme case, when this quantity A times xx approach to infinity, is only to view the question, r is approach to infinity, and C, the center of rotation, approach to infinity. When instead E times xx approach to 0, we have the opposite. The beam is completely bending, and we have a small radius, and C approach near to beam. So here C approach to infinity, here C is next to the beam, and the radius is very low, and the radius is very short. So, but we don't have this extreme case of flexural stiffness approach to infinity or flexural stiffness approach to zero. In some case we stay in the middle of these two consideration, because we can make for, as said before, for little angle an approximation like this of a certain radius r, a location of a rotational center at certain point. So with this we have completed the study of this the study of pure bending applied to a beam. In the next video we will see an exercise, two exercises about this stuff. So I hope that this lecture can be to support, and we will see to the next video. Bye.